Good day, ladies and gentlemen. My name is Chukwuemeka Awah, Department of Electrical and Electronic Engineering, Michael Akbar University of Agriculture, Umudike. I wish to present a paper titled Electromagnetic Performance of a Two-Stator Permanent Magnet Machine. The paper ID is 005. The presentation will follow this pattern. 1. We'll look at the abstract, then the background of study, methodology, before discussing the results, and then conclusion with some recommendations, and of course with reference. Under the abstract, we'll have some key points. 1. We designed and developed a permanent magnet machine which has dual stator. By that we mean a set of two different stators with a single rotor sandwiched in between the stators. In the course of the work, we will consider some machine parameters, and the considered elements are 1. The air gap flux density, the magnetic coercive force, flux linkage, output torque, torque report, total harmonic distortion, which is the THD, losses, and of course with the efficiency. Also, we'll observe that the proposed machine has better output torque than its single stator counterpart. More so, it also has lower total loss and improved efficiency than the single stator equivalent when compared. Overall, the investigated machine is suited for high torque, low speed machine operations. A good example is found in in-wheel direct drive application. Looking at the background of study, the machine, the two-dimensional structural arrangement of the machine is as presented here. We have the outer stator, while we have partitioned inner stator. The red and blue elements are the PMs, the permanent magnets. The cup with a ring is the rotor, which serves as the modulator. Overall, the dual stator has 6 slots in the outer stator, and it's equipped with 3-phase windings. The number of protopoles in this machine is 13. We'll have about 72 number of turns per phase. The machine is a small size machine with about 90 mm diameter, and of course with 25 mm active length. It has 2 air gaps. One is here, then the second one is here. It has a negligible reluctance torque. On the course of the investigation, we found out that the reluctance torque of that machine is negligible. And it has 2 different operating principles. One is the magnetic gearing principle and the flux switching principle. Overall, this machine delivers high torque at low speed. Of course, we've mentioned before that it's suitable for direct drive applications and could be applied in power generation and in-wheel vehicle applications. However, it has some flaws. 1. The scarcity and high price of the PM magnets is a disadvantage. The machine could be demagnetized, especially when overloaded, as well as at high temperature. It also has some complicated manufacturing issues, especially when manufacturing the cup rotor. The methodology will actually employ the two-dimensional finite element method using Maxwell software, which is in collaboration with the ANSYS and ANSOFT. Yeah, the machine is excited with three-phase current excitation, sinusoidal current, which we can see here with 120 degrees displacement. That's exactly when you excite the machine, then the flux linkage, which will emanate as a cause of that, will yield the EMF, which in turn will produce the output torque. In considering the losses, we'll employ the standard iron loss equation, which we can find here. And of course, when considering the efficiency, we'll look at the total power given by the machine divided by the sum of the total power with the overall total losses, which includes also the copper losses. In discussing the results, we'll have some results here. If you look at the results, we'll have the total harmonic distortion and torque ripple in one graph. The developed machine, it has about 2 THD, which is reasonable, and a torque ripple of about 10.4, which is also within range. We'll try to compare the results obtained from this machine with the conventional single stator machine, and we found out that the proposed machine has over 30% larger output torque than its single stator equivalent, as we can see from the graphs here. Yeah, still on the results, we also looked at the losses, and we'll consider the iron losses in the rotor, the iron losses in the stator, and then looked at the overall efficiency of the machine. And as well, on comparison, we found out that the developed machine or the proposed machine also has better efficiency of about 86.1 as against 83.2% of the single stator equivalent. However, we should note that when we make use of the SMC, the soft magnetic material, the core losses of any given electric machine could be reduced as given in literature. As well, we can reduce the permanent magnet eddy current losses obtained in this machine by segmenting the PMs into tiny partitions. Literature shows that when that is done, the PM losses, which is the eddy current loss, could be reduced, and that could go a long way in increasing the of the machine. In conclusion, we have developed a novel dual stator PM machine, which we have proposed and presented here. Of course, the proposed machine is capable of producing larger torque than the single stator counterpart. It has better efficiency compared to the single stator type. And of course, when you talk about the PM usage, the output performance of the machine as against the PM or permanent magnet consumption, you found out that the proposed machine outweighs that of the single stator type, even at high electric load. We recommend some future works which can be carried on this. For example, one, we recommend that the experiment should be carried out when the machine is prototyped in order to validate the work. We can also consider analytical modeling of the proposed machine. Of course, the magnetization withstand capacity of the PMs can also be investigated. And finally, PM reduction is very important. Loss reduction is very important. We can consider that, especially during the optimization of the machine. Some references used in the paper are listed here.